Hi guys, it's Mrs. B. So here's your lesson for Wednesday, April 1st. Piecewise word problems. So the last 2 days we talked about writing piecewise functions, graphing piecewise functions, and today we're going to talk about piecewise word problems. I think you'll find today's lesson a little bit easier than the last couple lessons. So by the end of today, you should be able to analyze the information given from a piecewise function or graph and write a piecewise function for a given story. So, when we look at a graph, every graph tells a story, right? A piecewise graph could tell us a lot of information about a certain situation. So if I read this problem, it says, Jackson traveled his elevation over time while skateboarding up and down a ramp. The graph displaying this data is a piecewise linear function represented below. So you have to keep in mind the entire time when we're reading through this is that it's a skateboarder that's going up and down a ramp. Okay? So for part A, it says, explain what might have happened in the interval from 10 to 16 seconds. So it's asking, what is happening from the interval from 10 to 16 seconds? So this one right here. Okay? We have elevation on the y-axis and time on the x-axis. So, from 10 to 15 seconds, okay, we notice that time is going down and so is the elevation, right? As he's traveling down, as the line goes down on the graph, so is the elevation. Okay? So, you can say something like Jason was skateboarding down the ramp. Part B says, when does Jackson reach his maximum elevation? What was that elevation? So we want his maximum elevation, and what was the elevation? Well, it looks like on the graph here, his maximum elevation, right? If we look at elevation, this is elevation here. The maximum point was here, which is, if we go over 6. You might have to fill in some of the numbers. I think it's a good idea to write in some of the numbers. So his maximum elevation was 6. So, and that is at time 10 seconds. So at 10 seconds, he reaches 6 feet. Part C says, identify 2 different times that Jackson's elevation was exactly 3 feet. So 2 different times his elevation was exactly 3 feet. Well, if I go over to my graph, elevation is on my y-axis, so I have to find 3 feet. 1, 2, 3. So here's 3 feet, so I'm going to go straight across, and anywhere that graph touches my orange line, those are the 2 times that he reaches 3 feet. So at time is 1, 2, 3, 3 seconds, and 10, 11, 12, 13 seconds. So at 3 seconds, and we can abbreviate, and 13 seconds. D, what was Jackson's elevation at 11 seconds? So I look at my graph, and I find 11 seconds. Right, here's 11, and I go straight up to the graph. Okay, so the elevation at that point, if I go all the way over to the y-axis, is 5 feet. For what total time is Jackson's elevation increasing? So if we look at the graph again, I want to know, where is he increasing? So he's increasing in elevation from here to here, and he's also increasing from elevation from here to here again. So that's from, let's see, time is 0 to 4 seconds. So 0 to 4 seconds. Let me get rid of these markings here. And then we have 6 seconds to 10 seconds. Okay, so from 0 to 4, that's 4 seconds. And from 6 to 10, that's another 4 seconds. So total is 4 plus 4 gives me 8 seconds. Letter F. For what total time is Jackson's elevation 4 feet or higher? So total time, he's 4 feet or higher. So let's go to the graph. 4 feet is 1, 2, 3, 4. So I'm going to go and I'm going to cut everything else off. So I only want the time intervals that he's 4 feet or higher. Well, let's see, he starts at 4 feet here at 4 seconds. And he's still at 4 feet, still at 4 feet, still at 4 feet, right? All the way to 12 seconds. So from 4 to 12, well, 12 minus 4 is a total of 8 seconds. Okay, so that's how we read a piecewise graph. Number 3. The graph below models Craig's trip to visit a friend in another state. In the course of his travels, he encounters both highway and city driving. So he's driving a car, right? We have miles traveled on the y-axis and we have hours on the x. Based on the graph, during which interval did Craig most likely drive in the city? Explain your reasoning. Well, if I look at the graph and we just look at some of the lines here, okay? From point A to point B, he's traveling, he travels 110 miles in 2 hours. Okay, from C to D, he travels 110 miles to 200 miles in approximately 1.5 hours. And then D to E, okay, he's traveling less miles. He's only traveling about 30 miles in 2 hours. The real thing that you need to look at here is which slope is the least steep where he's still traveling. Okay, based on the graph, during which interval did Greg most likely travel in the city? Okay, if you're traveling in the city, you're not traveling as far because you're stop, go compared to highway miles, right? So the one that's least steep, we have to be careful. B to C and D to E. Okay, those are the two that are the least steep. However, if you have a horizontal line like B to C, that means he's not moving. Okay, he's not increasing in miles, right? We're not increasing or doing anything in miles, so he's not moving. So it can't be that one. So his city miles are probably right there. Okay, from D to E, because he traveled at a slower rate. Okay, the slope of the line is less steep. Part B says, explain what might have happened in the interval between B and C. Well, B and C, right? We're not increasing in miles traveled, so he was stopped. Okay, he did not increase in miles at all, therefore he wasn't moving. D says, determine Craig's average speed to the nearest tenth of a mile per hour for his entire trip. Now this is the one where we have to be careful, okay? If it says for his entire trip, his average speed, what it's really asking us to do is to find the slope for the entire trip. So from point A to the final point E, what is the slope? So if we had an imaginary straight line, okay, we want to know the slope from A to E. So remember, slope equals y values over x values. So all I'm going to do is I'm going to count. How many do I have to go up and then over to get to E, from A to E? So I have to go up all the way to 200 and it looks like Might have made a mistake. I might have drawn over the line too much here. All the way to 230. So my y value is 230. Divided by, now I have to go all the way over to E. Remember, we can't just count boxes. You actually have to look at the bottom, at the x-axis. Okay? From here to E is really, let's see, 7 hours. So 230 divided by 7, if you do it in your calculator, gives you approximately 32.857. Rounded to the nearest tenth. Well, here's my 10th place, so I cut everything else off. 5 or above, give this number a shove. Okay, so since this is a 5, it is 5 or above, so we give this a shove to 9. So our answer is really 32.9 miles per hour. Two more for today, guys, and then we'll call it a day. A storm passed through Schenectady, New York on January 20th, 2014 that dropped snow on the ground over a period of time. So snow was falling on the ground. There was no snow on the ground when the storm began. At 12 p.m., this is important, snow fell at a constant rate of 1 inch per hour for 2 hours. Snowfall stopped for 1 hour. For the next 2 hours, snow fell at a constant rate of 0.5 inches per hour. For the last hour, snow fell at a rate of 1 inch per hour before the storm stopped completely. Use this information to complete the following parts. So part A says, graph the piecewise function described above. Okay, so now we have to actually take the information that we just read and draw it on the graph. So what I'm going to do is I'm going to actually highlight this in different pieces for you so that it's easier to see what we're graphing. Okay, so the first piece said, okay, there was no snow on the ground when the storm began. Okay, so that means we are starting our graph at 0. There's our first point. The second piece says, at 12 p.m., snow fell at a constant rate of 1 inch per hour for 2 hours. So 1 inch per hour. So let's look. Okay, we're starting at 0, and we're going at 1 inch per hour. So on hour 1, we have 1 inch. And it did it for 2 hours, so we go to hour 2, and we should have another inch accumulated. Okay, connect the dots. Straight line. Second piece, snowfall stopped for 1 hour. So it stopped for 1 hour. So we shouldn't be increasing at all on the line. So from hour 2 to 3, it stopped. Third piece. For the next 2 hours, snow fell at a constant rate of 0.5 inches per hour. So for the next 2 hours, so from hour 3 to hour 4, we accumulated 0.5 of an inch. So if we look at the graph, we actually have, let's see, 1, 2, 3, 4. So this is 2.5. This is 3.5. Sometimes it's helpful to fill in some numbers. So I'm starting here and I'm going to a ½ inch, right? I didn't go to 3, I'm going to 2.5. So right here at hour 4. So that happens for 2 hours, so we need to increase by another ½ inch for hour 5. So there's my straight line there. Oops. I'm going to make that better. And finally, for the last hour, snow fell at a rate of 1 inch per hour before the storm stopped completely. So I'll make this one orange. 1 inch per hour before the storm stopped completely for 1 hour. So for the last hour, so one more hour, we accumulated 1 inch. So 3 to 4, and then I have to graph it on hour 6. Okay, so we did this. B, how much snow had accumulated by 5:30 p.m.? So now we just read the graph. It's that simple. So at 5:30 p.m., let's see, 5:30 would be right here. So I go up to my graph. That's right here. So 3.5 inches fell at 5:30. Part C. Over what interval was there exactly 2 inches of snow on the ground? So, I look at my graph and I find 2 inches of snow and I draw a line. Okay, so it's right here, right? So from hour 2 to hour 3, there were exactly 2 inches of snow on the ground. And part D. At what time does snow accumulation reach 2.5 inches? So I'm going to do the same thing. Okay, I'm going to look for 2.5. There it is, and I'm going to draw a line. The graph crosses that line right here. That is hour 4. So on hour 4. Okay, last one for today, guys. A driver leaves home for a business trip and drives at a constant speed of 60 miles per hour for 2 hours. 60 miles per hour for 2 hours. Her car gets a flat tire, and she spends 30 minutes changing the tire. She resumes driving and drives at 30 miles per hour for the remaining 1 hour until she reaches her destination. Part A. On the set of axes below, draw a graph that models the driver's distance from home. Okay, so look at our graph. We have distance on the y-axis, and we have time on the x. So, a driver leaves home from a business trip. So this is starting at 0. At a constant speed of 60 miles per hour for 2 hours. So, 60 miles per hour. So every 1 hour she goes 60 miles. So at hour 1 she goes 60, and then at hour 2 she goes another 60. So there's my first piece to my function. She gets a flat tire and she spends 30 minutes changing her tire. Well, we know the car is not moving, right? So for another 30 minutes, if we look at time, this was 2 hours and 30 minutes. So she's not moving, so we're not increasing the line at all. Okay, we're staying flat. She resumes driving at 30 miles per hour for the remaining 1 hour. So for the remaining hour, from 2:30 to 3:30, right, we're driving at 30 miles per hour. So if we look, 120, 150, each interval here is 30 miles. So for the next hour, she drives 30 miles per hour. So we increase that by 30. From here to here is 30. And then after that, at 3:30, she reaches her destination. Okay? So we did part A. Part B, identify the slopes for a line segments you drew for the given intervals. So for each interval here, we need a slope, and we can find that. Okay? So, from the interval from 0 to 2, okay, this one right here. What is the slope? Well, let's count, right? Slope, remember, equals y over x. So I need to count. How many up do I have to go to get to the next point? 1, 2, oh, well, it's really 30, 60, 90, 120. So we have 120 is our y value. Now I go over. How many? So we can't count the boxes. You have to actually look at the numbers on the x-axis. So that's 1, 2, right? This is 2. So 120 divided by 2 gives me 60. So in that interval, she went 60 miles per hour. Second piece. We'll do this one in blue. This one was in red. So the second piece right here in blue, Remember, that's a horizontal line. When we have a horizontal line, okay, our slope is 0. She's not moving. So it's 0 miles per hour, right? Not moving at all. Easy. And the last one in orange, okay, from the interval 2.5 to 3.5, well, how many do we go up on the y? Just 1, but remember that 1 is 30, right? 1 box equals 30 inches. So m equals y over x. Our y value is 30. Our x value, if I go over 2 boxes is counting as 1. Right? From 2:30 to 3:30, that's 1 hour. So 30 divided by 1 gives me 30. 30 miles per hour. Part C, determine the driver's average speed to the nearest tenth of a mile per hour for the entire trip. All right, from the entire trip. Let me get rid of some lines here. So from point A to point B, what is my slope? So really it's asking from the start to the finish. If I drew an imaginary line here, what is the slope of this line? Okay, so we're looking for m equals y over x. Well, let's count. I'm going from this point to this point. How many do I have to go up? 150, right? 150. So my y value is 150. Now I have to go over. How many am I going over? How many hours passed? Let's see. That on the x-axis is 3.5. 150 divided by 3.5 gives me 42.857. It says the nearest tenth. So remember, the nearest tenth is the first place after the decimal. So I want everything in over, but I first have to ask myself, 5 or above, give this number a shove. So this is 5 or above, so I give this a shove to a number 9. So really this equals 42.9 miles per hour. That is her average speed for the entire trip. Alright guys, remember to take a look at the assignment. Let me know if you have any questions. Good luck.